Hello everybody. Today's 9 sides of infinity for people learning calculus. We encounter a lot of infinity things in calculus, and I don't think this is a math textbook explain what the infinity is sufficiently, and that's why when you encounter many type of infinity in infinite series, you get confused. So let's talk about what the size of infinity. Okay, now we go back to the two little kids arguing. Okay, I know the largest number in this world, right? Another kid asked, what is it? This clever kid said, well, I learned calculus, so I can tell you. Whatever number you give me plus 1, oh, this is mighty number. You know, you cannot give any number. So give any number plus 1 is, of course, larger, right? But second kid was smarter. He said, well, I know even better number, the even larger number. And the kids asked, what is it? Whatever the number you give me plus 2. Uh-oh. The second kids win? What do you think? Who win? Any winner? So we are talking about infinity plus 1, infinity plus 2. What is this? This is infinity, right? This is also infinity, because whatever the number, it can be any number, any large number, which is infinity. Okay? Plus 1, plus 2, they are both infinity, so there's no winner. It sounds strange. Well, it's like the argument, the infinity plus something is infinity again. Why is that? Can you tell me? It's against what we learn from elementary school all the way to high school, the math, addition, subtraction, multiplication. Maybe you should say infinity square is better. This is again infinity. So you cannot win. How can you get this out? Okay. Well, some student in the calculus class ask, which is larger, number of positive integer or number of negative integer? What do you think? Which is larger? Well, are they same? Can you say equal? Okay, so we have learned the math based on this real number, which is all on this number line. 1, 2, minus 1. Why it's on the number line? It has a size. It has a location, even irrational number has a position. Okay? Only the number doesn't belong here is imaginary number, right? There's no position here. Well, we created imaginary number vertically, so we cover everything later when you learn the complex number theory. But so far we learn only everything belongs to real number. The infinity is not a real number because you cannot say it's here, right? Infinity is not real number. How about 1 over n, and n go infinity? It goes to 0. Is this a real number? It's 0 here. No, it's not. This is not 0. only you said limit zero, because limit means after you make n infinity, where does it arrive? Arriving point is zero. But this number is not zero. Okay? This is larger than zero. This is larger than zero. Right next to zero, but very close. How close? You cannot pinpoint where. So this is not real number, just like infinity. So infinity bring a new kind of number which is not real number. It's not imaginary number. You can have I infinity, then you have, here you go, imaginary infinite number. Okay, so why you cannot add, subtract or multiply infinity? Because, okay, when you compare number a and b, you subtract, then you can tell a is bigger or b is bigger. So it's a subtraction operation, math operation based on assumption. You have a and b are both on number line, means a has a size, b has a size. Okay, so infinity minus b, or a plus infinity, infinity doesn't have a size. It's just the size that bigger than any number. That's the kind of size. You cannot do this operation. Okay, so in math, carefully we use this notation n equals infinity, right? So when you say n minus b, it's some number, but once you say n goes infinity, then this becomes infinity. A minus n has some number, but when n goes infinity, then become negative infinity. Ooh, infinity has positive, negative. Oh, that means positive infinity is larger than negative infinity. Sounds like we have some hope. We have a size infinity here. So you think about, if you cannot use subtract, how can you compare the number which is larger? Okay, when you compare the number, we go back to the kindergarten. You say number of orange and number of apple. We have this many orange, we have this many apple. Okay, so you don't do 4 minus 3. You don't need this. What you do is you correspond each, and what is left here indicate which number is larger. Number of apple is larger than number of orange. So you don't need subtract or any math. You can just compare by correspondence. This is how the very basic way to compare which number is larger. Okay, without any mathematics, you can compare. Okay, so let's compare number of positive number and number of negative number, right? 1 minus 1, 2 minus 2, 3 minus 3. We correspond this and this. Okay, so we correspond this and this, this and this. Seem like if 0 is included in positive number, number of positive number is slightly larger than number of negative number. Is that right? Because 0 is included in the positive number. Well, it may include it in both, then it's the same. Can you say this? Well, actually, you're talking about infinity plus 1. This is the same infinity, so you cannot say which is larger. But at least you can tell they are very close. You can do correspondence, right? Does this work? Let's expand this idea, right? 1, 2, 3, 1, 2, 3. You have an intersection. Okay, so number of intersection here, including this number of intersection and number of positive integer, which is this guy and this guy, this guy, which is larger? Well, you look at this. For each number, you have an infinite number of intersection. So you can say this guy must be really big, bigger than this one. Can we say this? Well, actually, you take this number, sticker, put the sticker here, 2. And 3, 4, 5, 6, 7, 8, 9. You keep putting sticker this way. Then it's every intersection is corresponding to this integer. Is that fair? Is that fair to do? Well, according to the comparison principle, if you can make one-to-one correspondence, then it should be the same number, right? Well, so you get the sticker from number of positive integer. You keep putting a sticker this way. You can keep going forever, infinite number. So you're done. You made one-to-one correspondence. That means number of integer, number of this is it's a similar question like a rational number. Rational number is P over Q. This is integer, and this is integer. And to make the argument simple, make it a positive integer and a positive integer here, okay? So you have like 1 over 3 or 3 over 1, 2 over 4, whatever, right? So this number of intersection is like rational number. The rational number and this integer, number of integer and number of rational number, is that same? See, this can be this line, okay? The 2, 1, and 0 over 2, 3. So you can have this side P, this side Q, okay? Then you can create all the intersection represent the number, rational number. So rational number, number of rational number is same as the number of integer, positive integer. Okay, so again, it's kind of weird, right? By looking at, oh, it's definitely rational number is much, number of rational number is much bigger than number of integer. But if you can do correspondence 1 to 1 forever, then you cannot say which is bigger. They should be same at least, right? Well, so when you go infinity, everything's fuzzy. How about real number? That include irrational number and rational number, right? That's going to be a little bit tough because every rational number you can attach square root of 2, become irrational number, or you can attach square root of 5. So infinite number of this exist in the real number. There's no way you can make a correspondence using this rational number. If you figure out how to make a correspondence, the answer change. But since we cannot make a correspondence, real number is bigger infinite than the number of rational number. So the size concept change. Size 3 or size 4, it's easy, right? Difference is 1. The size difference is 1. But infinite has a size, but infinite size is like this type of infinite is larger than this type of infinite. So if you take infinite from this type, real number infinite, it's going to be number of rational number is going to be small. So this is a type of the number of real number and the number of rational number. You compare this, so definitely this infinite is larger. So infinite has a size, but it's not like the real number we learned so far, 3 and 4. The difference is 1. Not like that. So everything go infinite is okay. Suppose there's a 1 kilometer pass. 1 kilometer. And the ants here, the food here, okay? And the ants need to go there. These ants need to walk 2 kilometers. But if this ants go direct, he may miss it. But if he keep, the sunlight directions, get direction right, he may be able to go straight, right? Then square root of 2, 1.4 kilometer. It save a lot on the very hot summer day. He doesn't want to walk 2 kilometers. So this ant, he learned calculus, right? He said, I'm going to go halfway, go vertically halfway, go here. Okay, it's still 1 kilometer and 1 kilometer. Okay, I'm going to chop down this n, use the trick of infinity. So I go 1 over n distance, okay, and go vertically 1 over n distance, right? and I repeat this, get very close as 1.4, this straight line, then I can save the path. Okay, that's what he thought. The how many of you need 1 n of 1 over n for horizontal and n of 1 over n for vertical, right? So it's going to be 2. So when you make n infinite, very close to this line, I'm walking almost this line, still walking 2 kilometers. What's wrong with this? This ant said, something wrong. If I make n infinity, it's almost like, it has a little zigzag, but it's almost straight line. So I should be walking only 1.4 kilometers, not 2 kilometers. But mathematically speaking, he is still walking 2 kilometers, because when n goes to infinity, nothing changed. Total of horizontal is 1 kilometer, total of vertical is 1 kilometer. So now you know n goes infinite. It doesn't affect some of them. You have to look at the detail, how it goes infinite. You have to see when you have in calculus, calculate area. You have to actually add up and limit n equals infinite. You have to calculate this, see if it's converged to some number. This converged to 2 kilometers. So this ant, no matter how big the n is, he's still walking 2 kilometers. Okay? So that's the kind of things about infinity. And I hope you realize that you are dealing with something new here in calculus, the new concept, infinity. Using this infinite concept, you're constructing entire calculus. Okay? So this calculus is kind of the witchcraft. Somebody put the ingredient called infinity and transformed the algebra into something called calculus. You have to know this ingredient infinity so that it's nothing magical anymore. I know this comes from infinity, the witch added ingredient infinity to the algebra, and that's what I'm getting here. And nothing to be afraid of once you know what the witch added to the ingredient. I hope you like this. If you like it, please subscribe. Wait for the next episode. Easy calculus.